Okay, so now we're going to talk about compounds, right? We were specifically just talking about atoms. Now we're going to talk about compounds. We're going to be able to do this same sort of thing. The only trick is we're going to have to figure out what the molar mass of our compound is. Okay, actually pretty straightforward. First of all, there's some terminology that I don't really think is all that important. If you're talking about a covalent atom, it should be the molecular mass. Whereas if you're talking about an ionic compound, it should be the formula mass. I think that this is dumb. I mean, we're just going to call them the molar mass for whether it's ionic or covalent. There's no point in having two different terms for it. It's just going to be confusing. Okay. Anyways, either of these are going to be considered the molar mass, whether it's ionic or covalent. I guess good to know for an ACS exam if they're trying to be tricky, but molar mass is the more commonly used term. So I don't know why they're trying to do that for us. Okay. Anyways, how do we figure out the molar mass for something like H2O? Right? If we were talking about the molar mass of just hydrogen, I would know to look on my periodic table. That's the 1.00794. That's the molar mass of hydrogen. If I was talking about the molar mass of oxygen, I would know where to get that from the periodic table as well, right? But if I'm talking about H2O, now I'm going to have to combine these pieces of information in order to get the molar mass of H2O, okay? And it's pretty straightforward. You're just going to take the molar mass of the hydrogen, right? So in this case, they don't use all of our digits from our periodic table, but that's because this is from the lecture slides. So when you're doing this calculation at home, you're going to make sure you've grabbed all those digits from the periodic table. This would be the molar mass of hydrogen. Okay. And then you're going to grab the molar mass of oxygen. Again, they didn't pull all those digits, but you're going to make sure to do that when you're doing it at home. So notice that we're getting the molar mass of H2O from the molar mass of oxygen and hydrogen. We're going to combine them together. Right? And since I have two hydrogen atoms in H2O, I'm going to make sure to take that quantity and multiply it by 2. And then I'm going to add it to the one molecule of, or the one atom of oxygen, right? So I have two hydrogens, so I take that molar mass and multiply it by 2, and then add it to the molar mass of oxygen. And this will give me a molar mass of 18.016. They're talking about it in AMU, so that's what it would be if it was just one molecule of water. But of course, we know that quantity on the periodic table also corresponds to the molar mass. So we can change those units to grams per mole, right? And that would be this 18.016. That'd be how I would convert from moles of water to grams of water, or vice versa. All right. And we can do the same thing with the ionic compound. Again, you're just going to pull the molar mass of, in this case, sodium from the periodic table. You're going to pull the molar mass from chlorine from the periodic table. And in this case, it's a 1-to-1, 1 sodium to 1 chlorine. So I don't have to multiply anything by 2 or anything like that. I'm just going to add them up together. And that gives me this quantity here. And again, we know that it's not just corresponding to the average atomic mass anymore. It's the grams per mole. This is the molar mass. So if I had moles of sodium chloride, I could figure out how many grams I had, or vice versa. If I went and massed out 10 grams of sodium chloride on the balance, I would be able to use this and figure out how many moles that is. Okay. I guess real quick, just to note, I wrote it like this with units grams per mole. This is the same thing as saying 18.016 grams per 1 mole. Right? This is kind of how you would write it in that more condensed form if you were just reporting it as an answer. And this is how you would write it if you were going to use it as a conversion factor in some sort of a math problem, or what we call stoichiometry problem. Okay. So it's two exactly equivalent ways of same piece of information, just written two different ways. Okay, yeah, so anyway, this is that same thing basically. All right, so let's do some examples here. We're gonna do 2 of these. You could do the other ones on your own. The slides that I've given you work out all 4 of them. I don't wanna spend too much time because I don't think it's too difficult of a concept. So let's work on first calculating the molar mass of N2O5, right? So step 1 is I'm gonna go to the periodic table and I'm gonna find my 2 elements. So we'll do nitrogen and oxygen, right? So I got to copy down both of those molar masses. So for nitrogen, it's the 14.00674. Again, we're writing all of these digits, so please get in that habit. This is the molar mass of nitrogen. Actually, the other way to do that is big M, nitrogen. The 15.9994, that was the molar mass of oxygen. So molar mass of oxygen. And now I'm going to add these together, but before I do that, I'm going to make sure to multiply by each of the relevant subscripts, right? So there's 2 nitrogens plus 5 oxygens. So this is what I'm going to punch into my calculator. And again, you're going to get in the habit of running this all into one thing. So 2 times 14.00674 plus 5 times 15.9994. Making sure to do that all in one shot. I promise it'll save you an error. And what we get is 108.01048 grams per mole. Okay. Truthfully, we should be really good about sig figs, and this is a mixture of multiplication and addition, which makes the rules for sig figs a really big pain in the butt. We're not going to worry about that. What we're going to do is just make sure to copy all of the digits given to us. And if we do that, we won't have any sort of a rounding error to worry about, okay? So even though we should be good about sig figs and keeping track of sig figs, from the purposes of my class, I'm going to say don't worry about it as long as you're copying down every single digit from the periodic table. And we're going to use every single digit from our molar mass that I calculated. Okay, so and again, just to sort of point out, this would be a term that I would use to go from grams of, what is this, dinitrogen pentaoxide to moles or vice versa, right? So if I wanted to use this term that I just calculated in an equation in stoichiometry, I would convert it to the form 108.1048 grams over 1 mole. And again, talking about that N2O5. Okay, so yeah, so these answers that you get, they're actually conversion factors. You can set them up just like this, and that's how we would use them, just like we did before in our stoichiometry. All right, so then the other one that I wanted to do was Mg, Cn2. What we're gonna do is, again, going to our periodic table, we have Mg, C, and N. Those are the values that we're going to need to grab from the periodic table. Mg was 24.3050, right? And then we have the 12.0107, and then nitrogen was 14.00674. Right, those are the values that we grab from the periodic table. Now we're going to make sure that before we kind of just add all these up, we multiply them by the relevant subscript. Notice that this 2 is going to apply to both the carbon and the nitrogen because that was in parentheses. So I'm going to have to make sure to do 2 times the 12 plus 2 times the 14, and then run that all together. So again, get in the habit of putting all of this together in your calculator in one shot. And you would get, and again, for the purposes of these molar masses, we're just going to copy down every digit that's given to us. So in this case, you get 76.33988 grams per mole. Cool. So just like we saw before, we can use these molar masses. These are now the molar masses of compounds, but you use them in the exact same way. You can go from grams of, for example, water to moles of water. You can even make that second jump to particles of water or molecules of water, etc. Okay. So here is just a sample calculation where they went from 500 grams of water to molecules. And the whole point of this slide is to kind of emphasize to you guys that you should be trying to do this all in one step, right? So the real way to do this would be to build it on the paper, meaning lining up those conversion factors the way that they should go, and then punching it into your calculator all in one shot, then going in back and crossing out units. And then the one thing that they didn't do here is 500 only has one sig fig. So they should have taken this answer and rounded it to one sig fig. Okay, let's do a few examples here and we can try to work on this, doing it all in one shot thing. Okay, so first of all, how many moles of CO2 are in 10 grams of CO2? So the first thing I got to do is figure out the molar mass of CO2. All right, so molar mass of CO2 is going to equal, going to my periodic table, I need to pull each element. So carbon, that's that 120107, and then oxygen, 12.0107, plus 2 times the oxygen's 15.9994. I've been working with these molar masses for a really long time, working with this periodic table for a really long time. So some of them, like carbon, I just have memorized. It might take you a little bit longer or a little bit more double checking to make sure you have the right answers. That's perfectly fine. Okay, so don't expect to necessarily do it at full speed like me quite yet. We're working up to that. Right, so then punch that in and we get 44.0095 grams per mole. That's the molar mass of CO2, right? So that's step one for this problem, is we got to figure that out. Now I'm going to use that quantity to help me convert from my 10.00 grams of CO2, multiply by that molar mass, and I'm going to do it in such a way that I put the grams on the bottom so that they cancel out. Punch that into my calculator and I get 0.227223. I'm going to go back and make sure grams cancel out nicely with grams, and I'm left with moles of CO2. And then I'm going to worry about my 4 sig figs here and 4 sig figs over there. So my final answer that I would report would be 2272 or 0.2272 moles. That would be my final answer there. Okay. What about if I wanted to go from moles of sodium chloride to grams of sodium chloride? Again, the first thing I'm going to have to do is figure out the molar mass of NaCl. I'm going to go and look it up for each one. The Na, that's the long one, if I remember correctly. Yeah, so 22.989770. Plus the molar mass for the chlorine, which was 35.4527. Oops. Add that together and I get the molar mass of sodium chloride, which is 58. All right, and again, really good idea to follow along on your calculator as I'm doing this. You might have to pause if I'm moving a little bit fast, but making sure that you're getting the same answers and you know where these numbers are coming from is really important. Okay, so that'd be grams per mole for the molar mass. So now I'm going to start with the quantity given, the 905 moles of NaCl. And I'm going to use the molar mass, but I'm going to make sure that moles are on the bottom so that they'll cancel. 8.44247, again, using all of my digits here so I don't incur any sort of a rounding error. I would get 52.8904. Then I'm going to pay attention to grams. Moles of sodium chloride cancel, and I'm left with grams. And then lastly, I want to make sure to round to 3 sig figs. So this would be 52.9 grams, right? Sig figs aren't going anywhere. We got to make sure that we're good about them. Okay, in this case, the 0.905 has 3 sig figs. That's the fewest of any in the calculation. So that's how many my answer should have. Okay, so that's how we can first figure out from the periodic table what the molar mass is for a compound, and then utilize that molar mass in converting from grams to moles or moles to grams. Okay, so now let's do the same thing for part A, but instead of figuring out how many moles I have, let's go all the way to molecules of CO2. Okay, actually, let me go back because I want to show you how similar it is to the setup that we had before. Now I'm going to go to molecules of CO2. So again, I'm going to start off with my 10.00 grams of CO2. And again, I don't want to just stop at moles. I want to go all the way to molecules. So I'm going to first convert from grams to moles using the molar mass that I calculated. And then I'm going to use Avogadro's number to take me from moles to 6.0221 times 10 to the 23rd molecules of CO2. Okay, so if I punch that into my calculator, I would get 1 point. I'm going to sort of do all the rounding and everything like that all in one shot to kind of move along a little bit quicker. I would get 1.368 times 10 to the 23rd molecules of CO2. Right, so now I've just noticed how this portion is the same first step, or I'm going from grams to moles. And now I have this second step where I make the jump from moles to molecules of CO2. So this is molecules of CO2. Okay, what if I wanted to go to actual atoms of oxygen, right? So not just molecules of CO2, but how many oxygen atoms do I have in that 10 grams of CO2? Then I make one more jump where I say that one CO2 molecule contains 2 oxygen atoms. Okay, notice where this came from right here, just from that CO2, from that molecular formula for the carbon dioxide. I have 2 atoms per molecule of CO2. So again, this is a really good idea to practice punching this all into your calculator to get one answer, sort of like what that other slide was saying. You don't want to stop at each individual step. You want to do it all in one. Best way to make sure that you're not going to incur any rounding error or make any copying mistakes. And if I did that, I would get 2.736 times 10 to the 23rd atoms of oxygen. Okay, so this conversion factor right here is another one that we're adding on here. I think it's pretty not too terribly hard to see how one molecule of CO2 contains 2 oxygen atoms. a little bit weirder or more difficult of a way to say this, if I had wanted to keep this in moles, I could have likewise said that there were 2 moles of oxygen in 1 mole of CO2. And this one is a little bit harder for people to wrap their heads around compared to the atoms to molecules one, although it's basically saying the same thing. If you had 1 mole of CO2, so 6.022 times 10 to the 23rd, then you would have 2 moles of oxygen, right? Because of the count. So whatever 2 times 6.0221 times 10 to the 23rd is. Both of these would have been conversion factors that we could have gotten just from that molecular formula, from that CO2. Okay. Similarly, this one is going to ask us for the number of magnesium ions and the number of cyanide ions. So let's try to figure out, and again, we're going to try to string this all together in one long calculation. Okay. The important one here is that we're going to have to go from, is it ions that they want? Okay. So we're going to be using these conversion factors where 1 MgCN2 molecule, it's really not called a molecule, it's supposed to be called a formula unit, but that's that point, the language is, I think it's kind of silly to distinguish between. So I'm going to be a little sloppy with my terminology, but that contains 1 Mg2+ ion, likewise 1 MgCN2 molecule, or really formula unit, if I was being better, contains 2 cyanide ions. So these are 2 conversion factors that we're going to have to use. Convince yourself that you can see where those came from. Okay, but the other thing we're going to need is the molar mass of magnesium cyanide. We actually calculated that one in an earlier slide. So I'm just going to be lazy and copy down our answer from there. 76.33988 grams per mole. That was our molar mass that we got for magnesium cyanide. All right, so then it wants us to go from 73.8 grams. And now I'm going to use the molar mass, but I'm going to put the grams on the bottom in order to convert to moles of magnesium cyanide. But it wants me to give an answer that's in number of ions, or number of particles, number of molecules. You could think of talking about very, very tiny quantities there. So I'm going to have to use Avogadro's number. Whoops. And then the last step is going to be 1 MgCN2 molecule gives 1 Mg2+ ion. Okay, so if I do that, punch it all into my calculator, I should get 5.8217 times 10 to the 23rd. And this is now talking about ions. If I'm going to be good about sig figs, which I definitely have to be good at, you can go 5.82 times 10 to the 23rd ions. All right, so see if you can't set it up yourself for the cyanide ions. I'll tell you right now that the correct answer that you should get rounded to the correct number of sig figs should be 1.16 times 10 to the 24th cyanide ions. Okay, so I'm going to have you guys do that second part on your own, where you figure out the number of cyanide ions present. You're going to set it up very similarly, and if you do it correct, that's the number you should get at the end.